All right, thank you for having me. So this is a series of talks, I'm not really sure how many, on effective methods in fractal geometry. So the purpose of the talks or purposes that I'm trying to go for are first trying to present all of that information that one needs in order to understand how effective methods might be impacting their own subfield of fractal geometry. So it keeps cropping up in areas, especially related to incidence type problems, but also some others. And so if you work in one of those subfields of fractal geometry, it'd be good to at least understand the basics of what's going on. And so that's the first purpose. The second purpose is if you do actually are interested in effective methods, just lay a foundation so that it would, expedite further study of the topic. So not just like calculus, not expecting that everybody is going to be doing it for the rest of their lives, just some basic familiarity for the purpose of being a whole fractal geometry. All right, so I started by writing up one big ugly or collection of definitions on the board. This first little section here is sort of technical. It's the knowing what an engine is before you drive a car. It's something one needs to know about, but also something that one rarely uses. And I think the main point that I want to get across here is mostly just that you really can formalize the idea of a Turing machine. We'll get to the informal idea momentarily, but Turing machines really are these combinatorial objects that are intended to formalize the idea of an abstract computational device that can perform any function that one can reasonably say to be computable. So it can really be formalized as this 7-tuple where we have a collection of states, a collection of symbols, some more symbols, a function that takes states and symbols and maps them to more states and symbols, some distinguished states, the starting state, the accept state, the reject state, and you can explain exactly what each of these are. Each of these is finite, 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 finite. These are finitary computation devices. And rather than get into exactly what all these are, as I said, all I want to convey with this is that these are finitary combinatorial objects. The way one thinks of these is, okay, we have this bi-infinite tape called the Turing tape. I'll use my space inefficiently. That has, we can label as, let's say, -2, -1, 0, 1, 2, 3, and so on. And we take some finite sequence of symbols in our input alphabet. So let's call them pi0, pi1, up to pi, so capital M. Everything else is going to be blank. And we perform some sequence of computations. Roughly, we're applying delta over and over and over again. It's allowing us to manipulate this. And either eventually we enter the accept state, in which case that's the output of the Turing machine, or we either enter the reject state, or maybe we never enter either of those states, in which case we end up in some sort of infinite loop. Either of those cases, we say the thing diverges. So that's how to think of it intuitively, and I feel the need to insert an anecdote here. I once gave a talk on this to a graduate seminar, but some undergraduates were invited because there was a postdoc who was teaching fractal geometry in some sort of RU to these students. And I was using pi to denote like a program. And they were so confused the entire time. And they asked me at the end of it, like, what does this have to do with circles? And I was like, nothing, it has nothing to do with circles. And then I realized, oh my God, you think that pi is like 3.14. Anecdote, there's always somebody who's more confused. So these are Turing machines. To sort of cut to the chase and get to Kolmogorov complexity, which is what effective methods are all about. We just need to tweak these things a little bit. I'm going to leave a little bit of space here and say that an oracle definition an oracle Turing machine is like a Turing machine, but we have two extra states and we have one extra input. So with two additional states, let's see, I'm not using the board here, I shouldn't care. I'm gonna do this over here with states that we'll call the query state. So this is Q sub QRY, the query state, and the answer state, Q sub ans. And then we also get extra input. A is going to be a subset of, let's see, I'll make it a subset of the input alphabet. Let's see, so sorry, not a subset of the input alphabet, subset of all finite strings over the input alphabet. And the way to think of how this oracle works, again, we've already seen the ugliness, no need to go through it again. But the idea is that for an oracle Turing machine, we get an extra tape. Let's see, again, 0, 1, 2, and so on. Just for technical reasons, let's make it infinite in only one direction. At any point in the computation, we can start writing to this oracle tape. So I can start printing some string, sigma 0, sigma 1, up to sigma k. And then everything else is blank. And I can enter the query state and ask the oracle, is this string in this oracle? The oracle is a finite set of strings. I can ask, is this string in this oracle? It will print either a 0 or 1, so it'll erase the entire string in one step, print either a 0 or 1, and enter the answer state. So it'll be telling you either yes or no. If there's no 0 or 1 in our alphabet, just some pair of symbols to promote yes and no. All right, and then that sort of gets to where I want to go, which is for us, and I think this is almost always the case, we just want to take sigma to be 0, 1, and gamma to be 0, 1 using this line symbol. All right, and then I think the last two embellishments I want to put on this are the idea of being prefix-free and the idea of being universal. So we'll say that a Turing machine or an oracle Turing machine, either way. So I'll say an oracle Turing machine, OTM, is prefix-free if It only halts on right halt. And something like that. Yes, halts. Only halts on a prefix-free collection of strings. So if it halts on two different strings, sigma and tau. So if I input sigma, it eventually halts. If I input tau, it eventually halts. And if sigma is a prefix of tau, is a prefix, sorry, prefix of tau, then sigma is equal to tau. So prefix free means that well, that's what prefix free means. You can't have, say, 0, 0, 1, and then also 0, 0, 1, 0 in this halting set, because this one's a prefix of this one. So cannot also halt on this, can also halt on this. All right, last technical definition. I'm going to continue to use board space inefficiently. We'll say that an oracle Turing machine is universal if let's call this thing U. Is universal if for every oracle Turing machine M and for every oracle A, I can find some program such that when you feed that program to you, it simulates M inputted with this oracle A. So what I mean by that is, let's see, if this, then there exists some program pi that is a finite string. Such that I'll say U of about sigma pi is equal to MA of sigma for all sigma. So we can use U to simulate any other Turing machine. And maybe I should say there's a prefix-free variant in which we say, okay, U is a universal prefix-free Turing machine, oracle Turing machine, if U is prefix-free and for any prefix-free M, yada, yada, yada. Okay. Done with the technical definitions. Any questions before we get on to slightly less technical things? Again, this is just sort of the engine. Now we want to get to the car. Well, I guess the engine's part of the car. We want to start driving the car. We at least want to get to the steering wheel. Okay. Shall I just keep going with the analogy? All right. I'll say section 2, Kolmogorov complexity. How's the camera? Where does it stop seeing?
No, it sees you. I care about it.
All right, thank you. To less complexity. All right, so now getting to the interesting definitions. So given sigma and tau are finite strings, and U, the universal prefix-free Turing machine, is just fixed forever. We'll say that the Kolmogorov complexity of sigma given tau relative to an oracle A. So I'm just going to say Kolmogorov complexity of sigma given tau relative to an oracle A is the make it a little bigger. A sigma given tau. It's the minimum length of a program. So bars around pi means minimum length of a program pi. So pi is a program, meaning that it's just a finite string. And let's see, that universal Turing machine with A, when you input the string tau pi, that is equal to sigma. Okay. So what's written over there, Kolmogorov complexity relative to A of sigma given tau is the minimum length of a program such that when you feed that program to the Turing machine and you also give it like an initial side string that we call tau to just kind of boost the computation, get you started. The minimum length of such a program pi is the Kolmogorov complexity. All right, and I'll note here, so I sort of lied a little bit. One last minor technicality. We're going to choose. We're going to choose that universal oracle Turing machine that we fix forever and ever. We're going to choose it in such a way that it sort of optimizes this quantity. So, remark. We can and do choose you do optimize the Kolmogorov complexity for every oracle and every string. Meaning that if we were to interchange U with some other Turing machine, another universal Turing machine, then the quantity that we would get would be greater than or equal to this one up to an additive constant. So choosing it in such a way that it's basically better than every Turing machine in every conceivable way, up to the fact that you might be losing an additive constant, but additive constants won't matter. Is this like a theorem that you can do this? Yes, I should have mentioned that, yes. The fact that any of this exists, that you can find prefix-free ones, universal ones, all of this is a gob of technical theorems. They are all combinatorial in nature. So, you know, there's You can do it without any hand waving at all, but I don't know that they're very enlightening. Yeah, other questions? Okay, let's see, how am I doing? Not doing pretty terrible on time, so, wait, yes. We're at the 30 minute, right?
Well, we were 5 minutes late, so you can.
Okay. All right, so I think maybe. Yeah, I'm going to just go straight to Kolmogorov complexity of points in Euclidean space. So I'm gonna keep working over here. So we define Kolmogorov complexity of these finite strings. We want to extend this to Euclidean space so we can start doing our geometry. So maybe I don't want to lie to you. Is this really the last definition? I believe so. Yeah. So last definition, at least for quite a while, is the Kolmogorov complexity of a point x in Rn given a point y in Rm. Maybe I could actually say of x to precision r. Precision r. An equal number given y in Rm precision s. Apologies if you can't see the bottom of the board there, but I'll write the actual definition. So this Kolmogorov complexity of x relative, or sorry, x given y relative to some oracle A, where x is to precision r, y is to precision x, or sorry, y is to precision s. A little bit messy, but we can digest this. So it's going to be, let me make sure I have my maxima and minima right. Yes. So I'm going to say maxima over all z. I'm going to say what z is in a moment. Maximum over all z over the minimum over all. Yeah, all of programs. The lengths of all programs divided such that, well, we're going to identify each of these binary strings with points of Euclidean space. So I can think of a point x, if it's a dyadic rational, as being some finite sequence of zeros and ones. Maybe the first n bits of x are just going to be the first, what will I say? Something like if x is equal to, say, x0, how about x1 for xn? We can think of this as being 0.x11, x12, and so on. 0.x1 and see n1, right? And so we're going to think of these things as infinite binary strings in this way. You can sort of interleave these if you would like to make it a single binary string. So it would be like x1, 1, x2, 1, up to x and 1, then x let's see, 1, 2, x, 2, 2, and so on. So combine them as a single string your favorite way. We're going to take the minimum of all programs such that our universal Turing machine, when you input, when you input this z together with the 5, this is going to lie in the same dyadic square of precision r. Sidelines 2 to the minus r as the point x to precision r. So same dyadic 2 to the minus r cube as x. Where z ranges over all precision x approximates to y. So see, we need another one of these. The and the same 2 to the minus x cubed as y. Okay, that's a lot.
So it's finite directional, or it doesn't matter.
Sorry, what was that?
So z is finite directional, so it's end with 0, 0, 0, or it can be periodic.
Oh, yeah, that's a very good point. I guess it doesn't really matter. So traditionally one just says rationals of any sort. Let's say,
Yeah, because somehow, in my understanding, you require that these strings are finite.
yeah, and so you'll have to choose some encoding to make that work. Maybe if you would like, you can insert some capital M here. And that capital N tells you what the period is, something like that. Encode these things in some crazy, ridiculous way, and then add the theorem, show that no matter what encoding you do, the Kolmogorov complexity of these things only changes by constant. So, yeah, a lot of technicalities here. For now, we just really need for no, I'm going to take that back. We're probably going to be stuck with this full definition for our first application. All right, section 3. Any complaints before I move on to the next section? What is that? So yeah, the next section, and this is going slower than I thought, so I think we might only have time to really just get to the pointless set principle. Maybe just say a little bit about how it has been used, how it can be used, and then I think I'll have to start doing some actual applications, some real proof applications the next time. So the way that this comes into fractal geometry is the point is that principle. let's just take the Hausdorff dimension version. No, I take it back. Let's do the Hausdorff and packing dimension versions. So for every set E in Rn, we have, let's see. How about, let's make some notation. Let little dim a of x. So given some number, some vector x, let's let this be the lim inf as r goes to infinity of a r a x over r. So we'll call this the effective Hausdorff dimension. Similarly, capital lim a is going to be the lim sup we'll call this thing the effective packing dimension. The point set principle says that we can compute the packing and Hausdorff dimension of any set, not even just Borel set, any set, by finding a special oracle that minimizes this effective dimension of the most asymptotically complex point. So the theorem says that for every set A in Rn, we have that the Hausdorff dimension of E is equal to the minimum over all oracles A. I'll say a word about that in a minute. Of the supremum over all x in E of the effective Hausdorff dimension of x relative to A. And similarly for packing dimension of E is equal to the minimum over all A of the supremum over all x of the effective packing dimension. Point to set principle from just a single point roughly up to take a supremum, you can compute the Hausdorff packing dimension of n digits.
Sorry.
Yeah.
Just to be precise, key area x without y is just the same definition, just the.
Yes, thank you, thank you. Let's see, where did I already erase it? I don't know. So K R A of x is K R A the, I don't know, any precision of x given the energy state, something like that. Thank you. All right, questions about the, well, I'll repeat myself first. So we're looking for a special oracle that minimizes this sort of asymptotic complexity of the most complex point. Where by asymptotic complexity, we either mean the lower asymptotic complexity in the case of Hausdorff dimension, or the upper asymptotic complexity in the case of packing dimension. This really is a minimum. There are countably many oracles, but we can in fact, write this as an infimum and then find something that attains the infimum. And then also I might add that you may compare this to the pointwise dimensions of a set or measure maybe looks a little bit similar, and that similarity runs very deep. In some sense, this really is the idea that you can compute the dimension of a set simply by imposing the right measure on it, putting the right measure on it, and then looking at the effective dimension, or sorry, not the effective, the pointwise dimensions of that measure for points in that set. What we're effectively doing here, no pun intended, is just putting ourselves in that framework, but forcing everything into a language that Turing machines can understand. So we're sort of doing it with one hand tied behind our back, and the theorem says that even with this one hand tied behind our back, where we're forced to do the things that we would like to do in fractal geometry, but we're forcing it to be in this computable framework, we're still able to compute Hausdorff unpacking dimension. And sort of that's the big idea behind effective methods is you have these extra constraints in what you do. You're forcing yourself to work in this computability framework. And by having these extra constraints on what you're allowed to do, you actually get more information in the sense that, all right, if I'm trying to show that the dimension of a set is something S, and somehow I'm not able to show that it has some larger dimension T just by manipulating a Turing machine. There's some sort of information inequality that I'm violating, some algorithmic inequality. Then I can use this point to set principle to show that this thing doesn't have dimension T, it has dimension S. That's the basic idea of why this is a useful thing to do. All right, and I was going to prove this. It's one of those things that I don't know. It's like the construction of the real numbers. Everybody should see it once, or so I believe. I'm very biased about this, of course. Maybe I'll just say a little word about it, and if we have time to revisit it in another lecture, we can actually prove at least the Hausdorff dimension version. The idea is that you really want to just find this oracle, construct this oracle that gives you a good dyadic cover of your set E. So dyadic covers are always going to be countable. I can encode this countable thing in some countable database. And because I have this countable database that takes this potentially uncomputable set of dyadic cubes and makes it countable, or sorry, computable relative to A, then I'm able to do the exact same thing that we're always able to do, which is find a cover that such that the sum of the diameters raised to the whatever power is less than 1, something like that. So we really do just show that we're able to satisfy the definition of dimension in the sense that, you know, Hausdorff dimension is defined in terms of covers. We know that it suffices to look at open covers, you know, just some little trick where you fatten the covering elements. It suffices to use balls, yada yada. It suffices to use these computable collections simply by putting these, say, dyadic covering elements into your A, programming them into A. All right. Questions before maybe we get to an application?
Maybe, so the supreme over X over E, like, is this in a typical situation, like, is it going to be like a single X, which is going to attain, or is it going to be like a typical thing throughout the set where it's all equal?
Yeah, so it is going to be, typical X's are going to be very close. So actually, if this set has positive S-dimensional Hausdorff measure, then HS almost every point will attain the supremum. If it doesn't have that, then, you know, for every epsilon greater than 0, you know, HT of the set will have. If it has positive Hausdorff dimension in positive Hausdorff measure in its dimension, then yes, almost every point has that property. It has measure 0, then yeah, do the appropriate modification. Does that answer your question? Okay. So yes, typical points have this property. You know, they attain the supreme. All right, so I'm going to do the less interesting, I think it's a less interesting application. Because, well, I probably should have done it first anyway, although I had it planned second. I take for granted how many technicalities there are in all this. So application number 1, what section is this? Section 4, 3, 4. Application 2. Application. So just a simple, cute little distance set theorem. So theorem alt of the Wilson 2023, something like that. So let's E be any set in Rm. Let's fix some norm that I'll denote with, you know, double bars, subscript star. So any norm. And let's let x be any point in Rn. Then the pin's distance set of E relative to this norm with the pin at x. That thing is going to have a large Hausdorff dimension. Let's see. I'll move this off. And finish this statement. Yeah. Here. So then with, I'll say, Hausdorff dimension of the pin's distance set, and I'll just define this for good measure in just a moment. The pin distance set with respect to this norm, pinned at x of E, Hausdorff dimension is going to be greater than or equal to the Hausdorff dimension of the original set E minus and minus. And here, the pin distance set is defined as the set of all norm of y minus x, where y ranges over all elements of E. Okay, and so this it does generalize a result of Falconer. So in that capacity, I guess it's interesting, but if you really dig into the proof of Falconer, you can up it to that level of generality. So yeah, he really deserves credit. The interesting part, I think, is that this is short.
Something with the definition of it. So what's the little x or what's the?
Let's see. So yes, this
that's an x.
yes, sorry, that is an x. There. Yeah, and so maybe to make this, I'll leave that as just something for next time. I think the interesting thing is that this is sharp, and that's where we're going to start to actually use complexity in a very serious way. Whereas this maybe just sort of a cute little warm up. It's gonna be a few line proofs, so if you might allow me.
Yeah.
I think technically I have like 3 minutes left.
Yes.
Okay. 3 minutes, we can do it. Brief. Alright, so we know that the packing dimension of the unit sphere with respect to this norm is equal to n minus 1. And it's some convex surface. So there exists an oracle A, this is by the point to set principle, there exists an oracle A. And a point Z in this sphere, such that the effective packing momentum relative to A of Z is equal to n minus 1. So this is getting back to your point. I said that you can actually find one. We should introduce an epsilon if we really want to stick to the point to set principle, but since this thing certainly has a positive n minus 1 dimensional measure, we can forego the epsilon. All right, let's also choose our oracle to have one extra property. Let's say so the same oracle E, we can simultaneously fulfill both of these criteria. So if I have one set E and another set F, I can choose an oracle such that we obtain our supremum here and also there. So I'll also take A such that the Hausdorff dimension of our in distance set is equal to the supremum over all y of the vector. So I'm just going to choose A to do both things. There's a very simple argument that you can do this. The idea, a countable database and another countable database is a countable database. So there's nothing too spooky there. Now the idea is very simple. We're really just about done. If we write y is equal to x plus the norm of y minus x times z, where z is this unit vector, then the Kolmogorov complexity of Kolmogorov complexity at any precision of y is equal to the Kolmogorov complexity of x plus this norm of y minus x times z. If I know x norm of x minus y times z, then certainly now addition and multiplication, these are computable operations. So certainly if I know x norm of x minus y and z, I can compute y just using this equation. So AR plus some little bit, I'll just say plus a little bit. Okay, we're almost there. Now, since x was fixed and x contains countably much information, I can actually do one last little bit. I can program x into the oracle. I can just stick all of its digits in the oracle, and using that querying procedure, can always just get the digits of x. It's not a variable, it's fixed. So I can take my oracle and actually do three different things by having it do this, and then also sticking a in there. And then lastly, literally all you have to do now is divide by r and take lim infs. So divide by r. Big. Take lim inf, and you get the dimension of y is less than or equal to, well, the Hausdorff dimension of this plus the packing dimension of this. This thing is going to go to 0 simply because if you already know x, then it requires no inputs, or at least a trivial amount of input to compute x, given x. So plus 0 plus the dimension of this guy plus, well, z was an element of that unit sphere, that n-1. Apply the point set principle, taking supreme over all y, and you have I take the supreme over all y. This becomes Hausdorff dimension of e, and this becomes Hausdorff dimension of your distance. Okay, sorry for going over time.
Thank you. Questions, comments?
Yeah, so when you wrote that, so we have a view and you wrote u sigma pi or something like that. But shouldn't it be the other way around? Because when we have a prefix-free Turing machine, that basically means that it can determine where the input ends. But if we have a sigma first, then we cannot know where that would end without knowing the program. So I think that it should have been pi first.
Let me see, is that the case? That might be the case. I think more traditionally, I sort of swept something under the rug there. If you're going to be looking at pi and sigma concatenated as a single thing, you probably want some sort of pairing function. So pi sigma or sigma pi. Want some sort of pairing function that has maybe a sort of an escape character in between. So really, it's the same idea as a vector is not literally, one number relates to another number. It's so yeah, you might technically be right. I'll have to think about that for a moment. But
And I think the point of this whole point free thing is that we can just concatenate them and that will work. But well, of course, this whole point prefix free thing doesn't matter at all for this.
yeah, it has not come up at all. It only comes up in slightly more technical context that I guess we will get to later. But so far, if we had just used non-prefix free Turing machines, everything would have gone through exactly the same. Complexity, plain complexity and prefix free complexity only differ up to an additive logarithm precision. So yeah, that's a good point. I'll have to think about that. I actually did get that from Don Stoll's lecture notes. So I'll have to see if he knows.
Okay. Further comments, maybe from the internet? Then let's thank Ryan again.
Thank you.